We have studied exceptions and interruptions, and we have discussed speculation as well when we talk about branch prediction, for example. And we have studied the pipeline design. The question now is, how do you process an exception or interruption, and how do you process speculation when executing in the pipeline design? This is what we're going to address in this lecture. So first, let's discuss exceptions in the pipeline. So an exception is just another form of a control hazard that happens during the execution of an instruction. For example, suppose that that the following instruction load x1 0, which means that I'm loading from the register 0, and the register 0 is protected and cannot be loaded from by a user program. So the execution of this instruction will produce a segmentation fault. So the question is, what should the processor do when such a segmentation fault occurs? So the instruction is the load word 00 into x1, and I want to prevent the value of x1 from being clobbered. I don't want the value that is in x1 to be changed, because this access is illegal. So this instruction cannot complete execution because it's generating an exception. But I want to allow all the previous instructions that were in the pipeline to continue execution to the end, because when the exception occurs and I want, for example, to examine the state of the program, let's say that you got a segmentation fault when executing your program with a debugger, you want to be able to inspect the state of the program and get the correct state for your program so that you can determine what was the bug in your program. So what you want to do is to flush the load word instruction from the pipeline. You also want to flush all the instruction that comes after the load word in the sequence of instructions in your assembly program. And then after you have done that, so you have completed the instructions that came before the load word, and you have flushed load word and all subsequent instructions, you're going to set the ucause in the UPC register values to the correct values, and then we'll transfer the control of the execution to the exception handler. So this is how an instruction should be executed, and you're gonna do something very similar, or actions that are very similar to that when you happen to have a mispredicted branch. That is, you made a branch prediction and you start executing instructions in a given path, and then you find out that that prediction was incorrect, and you find out that now you have to follow a different path. So the hardware that is used to support an exception, such as a segmentation fault, and to support the mis-speculation of a branch is the very same hardware. So let's look at our pipeline design. So let me move my picture to the upper corner so that we can look at the entire design. So this is the design that we have been reviewing now for a couple of lectures, and is the design of the pipelined data path with all the control signals that I need. So what I have now is a new flush signal that can be produced by the control unit. So the control unit can produce a flush signal that will control these MOOCs here and decide whether what should go to the subsequent units is the 0, which will make that operation a no-op, or whether it's the regular control signals. So notice that there is an OR gate here that will say that I'm going to send the 0 either if the hazard detection unit had detected that there is a hazard and therefore I need to squash an instruction, or if the control unit had decided that I need to flush the pipeline. There is also a new input for the program counter. In this case, the address is 1C09000, indicating that this would be the address where I go for my exception handler. So I also may be sending that address to the program counter to indicate that the next instruction that I should execute after the current one is the first instruction in the exception handler. This is how I, for example, execute an exception caused by a segmentation fault. There are exceptions that are what we call restartable exceptions. A restartable exception is an exception that occurs. The exception handler will handle the exception, and then you're going to restart the execution of the program. So the pipeline can be flush that instruction, and the handler will execute, then will return to that very same instruction. So that will be when there is some kind of temporary error that needs to be handled. So the instruction that caused the exception will then be restarted from scratch or restarted from the beginning of the instruction. The PC is saved in the user exception program counter, and there will be an identification of the cause of the instruction, and the actual value saved by in the PC is PC plus 4. So the handler will gonna have to adjust that. So if the handler wishes to re-execute the instruction that caused the exception, the handler will have to adjust the PC before returning from the exception handler. So here's an exception example. Let's consider this situation here, where I have the sub, the and, the or, the add, the set less than, and the load. And here is my handler. So let's assume that this add, for some reason, is caused an exception. If that add is caused an exception, what will going to happen in the sequence of execution is that I will have to execute the sub and the and the or. So I have executed the and, the or, and now I am the add, and the add will cause deception. So will cause the will set the values for the control for this instruction to 0, and will also determine that all the previous instructions need to be flushed. So the way you do that, one way to think about the way it occurs in the pipeline is that the add instruction that's caused an exception, most likely caused the exception during the execution stage, will raise a flag that is a flag saying I'm flushing the pipeline. And what will going to happen is that the pipeline will continue executing, and the instructions will keep propagating through the pipeline in such a way that the instructions that are ahead of that add in the pipeline will go to completion, and the instructions that the instruction that caused deception and the instructions that came before that will be flushed. So the way it happens is that all the control signals for the instruction that's causing deception and all the instructions that come before it in the pipeline, but they come after it into the logic of execution of the program, will be flushed. And so the actual execution does not start until the pipeline has been flushed, and there will be a signal that the next instruction to be fetched is the first instruction, the exception handler. So the situation in the pipeline is that when the OR instruction is in the memory stage, there will be 3 bubbles in the pipeline. That is the add, the set less than, and the load will become a no-op instruction. Those no-ops will propagate through the entire pipeline to the end, but they will have no effect in the state of the program, and then the execution of the handler will going to start. So this is a very simple way to handle exceptions in the pipeline. So again, the best analogy is to think that the instruction that's causing the exception is raising a flag, say I am an accepting instruction, I'm going to become a no-op. Every instruction that comes before me has to become a no-op, and we're going to start fetching the exception handler. So that works very well for a single instruction. But what happens when I have multiple exceptions in the pipeline? So the pipeline at any given time is executing multiple instructions. I could have multiple exceptions happening at the same time in the pipeline. One simple approach will be to deal with the exception from the earliest instruction first and flush out subsequent instructions. But I would like to have precise, and this would be a precise way to handle exceptions. In some complex pipelines, I can have multiple instructions that are issued in the same cycle, and that is called superscalar machines. And also in advanced designs, which we study in details in 49, we have out-of-order completion of the instructions. In these cases, maintaining precise exceptions may be difficult, and in some designs in the past, the processor would have what is called imprecise exceptions, where you could not really determine the order or the moment in which the exception happens. If you have imprecise exceptions, all you do, you stop the pipeline and you save the state, including the exception cause, and you let the handler work out which instruction caused the exception and which ones should complete and which ones should be flushed. If you have imprecise exceptions, you may require some manual completion of instructions. This simplifies the hardware, but it makes the software much more complex, and it's not feasible if you have complex multiple issue out of order pipelines, because it is too difficult for the software to figure out what was the cause of deception and which instruction should be completed and which instruction should not be completed. Therefore, in modern designs, we only use precise exceptions, where the precise exceptions, you can precisely determine not only which instruction caused an exception, but which instructions should be completing execution and which instructions should be flushed. Now we can talk about instruction level parallelism. Instruction level parallelism happens because you execute multiple instructions in parallel. For example, in the pipeline, you have multiple instructions executed at the same time. The idea is that you want to increase instruction level parallelism. One way that you can do that, you can construct what we call deeper pipelines. That's pipelines that have many more stages than the 5 pipeline stages that we have been discussing in 229. And actually, all existing processors have in the order of 14 to 18 stages these days. In the past, they had longer pipelines, but the high penalty of speculation led companies to reduce the length of the pipeline, but making deeper pipelines leads to more instructions being executed at the same time. So instead of having something like this, you have something like this. So this is a deeper pipeline. So you have less work doing per stage, you have a shorter clock cycle, so you can click through the pipeline much more quickly, and that leads to more instruction level parallelism and better performance. The other thing that you can do to increase instruction level parallelism is to have multiple issues. The idea is that you replicate the pipeline stage and you create multiple pipelines. So you start multiple instructions in the same clock cycle. So in this case, your clock per instruction will be less than 1 because there will be multiple instructions starting at the same cycle. So instead of talk about clock per instructions in such machines, we're going to be talking about instructions per cycle. And that's the measurement that we use in 49 when we're talking about the current designs, that they are all have multiple issue pipelines. However, the dependencies that you have in a program, the data dependence, will limit the instruction level pipeline that you have in Pretz. So the idea of the multiple issue pipelines, that instead of having this design where you have a single pipeline, you have a design where you have multiple pipelines that are operating at the same time, and you can have multiple instructions being fed to these multiple pipelines. So this is called a wider pipeline, and this is what's known as a superscalar machine. So multiple issue is the equivalent of having multiple starts of, for example, in our laundry, we saw the pipeline. This is the single pipeline laundry example. In the multiple issue pipeline example, we'll have a situation like this, where you have multiple, now perhaps you are at a laundromat, where you have multiple washers, multiple dryers, multiple stations of folding, etc. So this is what the super scalar machines that are the multiple issue machines would look like. So in multiple issue designs, you can have what's called a static multiple issue design. Those are also known as the very long instruction word machines, where you statically decide which instructions will be executed in parallel. This is done through compiler. The compiler will group the instructions that can be issued together and will decide statically at compilation time when generating the assembly code which instructions will be executed in parallel. And the compiler will package them in multiple issues lines. And the compiler will detect and avoid the hazards. So most of the work is done by the compiler, and the hardware is simplified in that way. The Itanium processor from Intel is one of the most well-known instances of this type of static multiple issue design. Unfortunately, the Itanium was not successful commercially for a number of reasons, but one of the reasons is that the compilers were not able to generate the kind of very efficient static multiple issues that the designers had hoped for, and because of that, the final performance of the processor was lower than what was expected when the design started. Another type of multiple issue is dynamic multiple issue. In the dynamic multiple issue, the CPU will examine the instruction stream and will choose instructions that can be issued in each cycle. So the data dependencies, control dependencies, all that are computed by the processor at execution time. The compiler can help by reordering the instruction and creating more opportunities for the CPU to extract more instruction level parallelism. The CPU, though, or the processor, will resolve the hazards using very advanced techniques at runtime. So those are the two ways in which you can increase the parallelism in the execution of the instructions. In both cases, you are using multiple issue. In one of them, you are relying on the compiler. In the other one, you are relying on the processor, the hardware, to identify that instructions can happen in parallel. The other topic that we need to discuss in this unit is the idea of speculation. Speculation is when you guess what to do with an instruction. And there are several types of speculation that we again discuss in detail in 49. The idea is that you're going to start operations as soon as possible, and you'll check whether your guess was correct or not. If the guess was correct, you will complete the execution of complete the operation, the execution is the instruction. If the guess was incorrect, you're going to roll back, and then you're going to go and you do the correct thing. This is very common both to static and multiple issues machine. For example, you can speculate on a branch outcome, and then you're going to roll back if the path is taken. You can speculate on a load. Sometimes you have a load and you don't know whether the load is to an address that could be changed by a store that has not completed yet, but you can go ahead and speculate the load and perform the load as if the memory will not going to change. And then if the location was updated after that load occurred, you will roll back and repeat the load. You can also do speculation when the address of the load was not completely finished, and you can guess the address that the load is going to go and try to start the load. Starting loads very early is very attractive for performance because loads can take a long time. So the sooner you start, then the better. You can also speculate on branch outcomes, but I'm going to stop at this part of the lecture, and we'll come back to a second part after a short break, because I think that will be better.